Good morning everyone. So, in this session we will see how the osmotic pressure modeling for membrane filtration can be done in order to get a appropriate system performance. In the last class, what we have seen is that we have looked into the transport phenomena based modeling for the reverse osmosis for flow through the porous medium, and we have found out how the solute flux, what will be the expression of solute flux and solvent flux through the porous media, that is the membrane. Now, as we have discussed in the last class, that is not the end of the story. One has to hook up the mass transfer boundary layer that is there, that will be formed in the flow channel. So, once that will be hooked up with the transport phenomena in the porous medium, then in the combined theory will be providing an estimate of system performance in terms of permeate flux and permeate concentration. Now, today we will be looking into the modeling of concentration polarization, that is the transport that is occurring external to the membrane surface in the flow channel, within the flow channel. So, we will be now there will be will be building up the model from a very simplistic approach to a very complicated one, and which will be quite realistic. So, therefore, first we will be assuming that there will be a constant film of solute that will be forming over the membrane surface, which will be having a constant thickness. So, this constant thickness film is known as the film theory, and it is one dimensional approach, and this film theory will be giving you an estimate of permeate flux and permeate concentration when it is properly hooked up with the Darcy's law and the solution diffusion model, or the definition of real retention, that will be the transport that is occurring within the within the membrane surface, within the membrane matrix. So, we will be first looking into a one dimensional model of mass transfer boundary layer within the flow channel. Then we will be looking into the shortcoming of one dimensional model and the film theory, which will be identical to the film theory, and then we will be looking into how these shortcomings can be overcome, and one can do a detailed modeling with a two dimensional modeling, and how the osmotic pressure control filtration will then really be modeled. So, at the outset, I will be doing the one dimensional modeling of concentration polarization. Now, the assumptions are basically it is a steady state transport process. Second assumption is the transport coefficients are constant. And third assumption is no solute adsorption . On membrane surface. So, now let us have a schematic and fix up our coordinate system. Suppose this is the membrane surface, and we are assuming a film of solute of constant thickness is formed over the membrane surface, and this thickness, constant thickness, is given as delta, and we fix up our coordinate system y from the bottom of the channel. So, this y is equal to 0, and this direction is x direction or axial direction. So, let us write down the various solute fluxes. Those are the appearing to the membrane surface. One will be the convective flux VWC, that will be the convective flux towards the membrane surface, because the solvent is flowing towards the membrane because of the applied pressure in the channel. So, because of that, some solute will be also dragged along with it. So, total solute flux towards the membrane by the convection will be VWC. Then there will be a backward diffusion from the membrane surface to the bulk. Why? Because solutes will be deposited over the membrane surface. Therefore, as we have discussed in the last class, the membrane solute concentration on the membrane surface will be higher compared to the bulk concentration, and therefore, that will cause a backward diffusion from the membrane surface towards the bulk. So, it will be minus d dc dy, and the solute will be going away from the membrane surface in order to whenever there will be some solute that will be coming to the permeate. So, it will be VWCP. So, at the steady state, summation of all three fluxes will be equal to 0. So, VWC minus of minus d dc dy minus VWCP is equal to 0. So, therefore, VWC is towards the membrane surface, VWCP is away from the membrane surface, therefore, there is a minus sign here, minus d dc dy is the diffusive flux away from the membrane surface. So, therefore, there is a minus sign here. So, you will be getting as VWC minus Cp plus d dc dy will be equal to 0. So, this one dimensional governing equation is formed in order to quantify the mass transfer boundary layer within the the solute concentration balance, solute balance within the mass transfer boundary layer. Now, let us try to solve this equation and see what we get. So, it will give you d dc dy is equal to minus VW C minus Cp. So, therefore, dc d by C minus Cp is equal to minus VW by d dy. Then this has to be integrated over the mass transfer boundary layer thickness 0 to delta and from membrane surface concentration to bulk concentration. So, you will be getting ln C naught minus Cp divided by Cm minus Cp is equal to minus VW delta by d, and if you take the minus sign incorporate. So, therefore, this will be giving you equal to VW by d by delta. And what is d by delta? D by delta is nothing but the film mass transfer coefficient. So, therefore, one will be quantifying the concentration polarization Cm minus Cp divided by C naught minus Cp is equal to exponential VW by k. This is a one dimensional model of to quantify the concentration polarization or mass transfer boundary layer in the channel. If we consider a one dimensional film that is formed over the membrane surface. Now, let us look into the how the mass transfer coefficient will be calculated or estimated. Then we will be looking into the how this will be hooked up with the Darcy's law in order to get a system performance and various simplified version of this. So, this mass transfer coefficient can be obtained from the non-dimensional Sherwood number relationship. K is obtained or estimated from the Sherwood number relationship. Sherwood is defined as K d equivalent by d, where K is the mass transfer coefficient, d equivalent is the equivalent diameter of a channel, of flow channel, and capital D is the solute diffusivity. Therefore, for a rectangular channel, channel of height, half height h and width w, one can estimate the equivalent diameter as 4 into weighted area divided by weighted perimeter. So, let us find out what it comes out to be. 4 into weighted area is basically, if this is the cross section of the channel, weighted area will be basically the 2 h multiplied by w. So, 2 h into w divided by weighted perimeter is 2 times w plus 2 h. Okay. So, this turns out to be, this 2 will be cancelling out, and generally h is in the order of millimeter and w will be in the order of centimeter, let us say 5 centimeter, 6 centimeter, like that. So, this will be order of magnitude 2 order of magnitude less. So, therefore, w is much greater than h. So, one will be getting this 2 h will be very small and w will be cancelling out. So, one will be getting d equal to roughly 4 into half height. So, that is the equivalent diameter of the channel, and for a tube or pipe, d equivalent is equal to internal diameter of tube. So, that is how the equivalent diameter is defined in both the cases for the flow through a channel or flow through a tube. Flow through a channel will be similar to flow through a spiral wound module, and flow through a tube will be basically the flow through a hollow fibers or flow through a tubular module. Okay. So, next we will be looking into the various relations of Cherut number expression for various flow geometries and flow domains, so that the mass transfer coefficient can be estimated. Now, let us look into the two domains. First, two flow domains, laminar flow, where Reynolds number is less than 2200, and for rectangular, and we will be considering two geometries, rectangular channel Reynolds number is equal to rho d equivalent velocity in the flow channel divided by mu. So, that is the definition of Reynolds number, and mass transfer coefficient will be estimated from k d e by d is equal to 1.85 Reynolds Smith d by L raised to the power 1 upon 3, where Smith is equal to mu by rho d. Okay, Smith number. So, for tubular module, for flow through a tube, Cherut number is defined as k d over d is equal to 1.62 Reynolds Smith d by L raised to the power 1 upon 3, where in both the cases L is the length of the module. That means, for rectangular channel L is the length of the channel, for the tube L is the length of the tube. So, mass transfer coefficient will be calculated from this Cherut number, and these relations are known as the Levex relation. For turbulent flow, where the Reynolds number is greater than 4000, the Cherut number relationship is obtained from famous Dittus-Boelter relationship. So, this becomes k d equivalent by d is equal to 0.023 Reynolds Smith Reynolds to the power 0.8 Schmidt to the power 0.33. There is no geometric factor like d by L. So, in case of rectangular channel, d is the d equivalent. In case of tubular flow, d equivalent equal to diameter of the tube. So, this becomes 0.023 Reynolds to the power 0.8 and Schmidt to the power 0.33. This relationship is famous Ditus-Boelter relationship. Correlation. Now, this correlation is obtained from the heat and mass transfer analogy, and it may be noted that for the Leibniz equations, these are basically the relations or equations, and these relations are obtained theoretical calculations from the fundamental theory, from basic principles, first principles. On the other hand, in the case of turbulent flow, Ditus-Boelter relationship is obtained from the correlations. So, it is not a relationship, it is a correlation, and it is generally obtained from the analogy between heat and mass transfer. Next, we will be looking into the how the Cherut number of mass transfer coefficients are estimated for starch cell, because in most of the membrane operations, the in laboratory scale operations, they are conducted either in starch cell. So, in case of starch cell, the Cherut number is defined as SH is equal to Kr over D, and R is basically K is the mass transfer coefficient as usual, D is the solute diffusivity, R is the cell radius. And we have two domains of Reynolds number. Reynolds number is defined as rho omega r divided by mu. So, omega is the angular velocity of stirring, RPM. So, it will be ultimately converted into radian per second, to be converted to radian per second. So, this will be having a unit of velocity. So, rho v r divided by mu, r is the radius of the cell. So, this will become rho omega r square by mu, where r is the cell radius. Okay. So, now we have defined Cherut number in two domains for Reynolds number greater than 30,000 and Reynolds number less than 30,000. In case of Reynolds number greater than 30,000, the relationship is SH equal to Kr over D equal to 0.0443 Reynolds to the power 0.8 Schmidt to the power 0.33. And in case of Reynolds number less than 32,000, this will be Cherut equal to 0.285 Reynolds to the power 0.55 and Schmidt to the power 0.33. These two relationship will be used in order to estimate the mass transfer coefficient in case of flow through a starch cell. Okay. Next, what we will be looking into? We will be looking into a system of cross flow filtration. What is a cross flow filtration? Cross flow filtration is basically a system which is generally used under in an actual industrial scale. We have the cross flow filtration. Why it is called a cross flow filtration? Because as we have discussed, suppose there is a flow occurring through a channel and membrane is placed at the bottom. In fact, in an actual module, there is in the top surface also you place a membrane, so that the surface area of the membrane is to be more in a small channel. So, therefore, one can get a very compact design, can realize high surface area in a small volume, and the design becomes very compact. So, let us just for the time being we assume a membrane is placed at the bottom surface, and this is the middle of the channel. So, this is half height of the channel. Now, when the flow is occurring, the concentration of the solute will be deposited over the membrane surface and it will form a mass transfer boundary layer, as we have discussed earlier. Now, the problem is this mass transfer boundary layer can grow unlimitedly, but if it grows unlimitedly, it offers more resistance against the solvent flux. So, therefore, at the beginning of the mass transfer boundary layer, the resistance is minimum and one will be getting a very high permeate flux. As the thickness of mass transfer boundary layer increases, it will be offering more resistance gradually and the solvent flux will be decreasing slowly and slowly. So, later on in the downstream of the channel, when the mass transfer boundary layer will be, growth of the mass transfer boundary layer will be very less. So, one will be getting a constant flux at in the downstream of the channel. So, therefore, what is cross flow? So, actually the feed is pumped into the channel and the bulk flow is occurring in this direction. So, therefore, the feed is entering into the channel, permeate is coming out and the retented strip is going out. Now, in this case, feed is flowing in this direction, in the horizontal direction, in the x direction, and if you call this x direction and this is y. So, feed is flowing in the x direction and the permeate is flowing in the y direction, which will be at 90 degree, or so that is why this flow is called a cross flow filtration. Why the cross flow term is coming? Because the filtrate or permeate is coming at 90 degree compared to the direction of flow in the feed chamber. So, therefore, in this cross flow filtration, what is the advantage? The advantage is we are not allowing the mass transfer boundary layer to grow unlimited. The mass transfer boundary layer is limited, the growth of the mass transfer boundary layer is limited or arrested by the convection, forced convection caused by the velocity of the feed in the channel. So, the growth of mass transfer boundary layer is controlled or arrested by the feed flow, and that is why in the cross flow filtration system will be very efficient and will be curbing the growth of the mass transfer boundary layer. Therefore, vis-a-vis the resistance against the solvent flux, therefore, one can realize very high permeate flux or the throughput in a cross flow system. So, cross flow systems, cross flow filtration are quite important and popular, and they are widely used in order to get in an actual membrane filtration system. In fact, all the spiral wound module, the tubular module, flow through hollow fibers, they are the cross flow systems. Okay. So, now we will be looking into the system prediction of system performance. Of cross flow system using the film theory, one dimensional model film theory and the osmotic pressure model. So, as we have discussed, there are two aspects in the modeling of this. One is the solution of mass transfer boundary layer in order to get the concentration profile. We evaluate this concentration profile at the membrane surface. Why? Because then it will be hooked up with the flow through the porous membrane. Evaluate concentration profile at membrane surface. Once this is done, then we will be having another transport flow domain. The next domain is transport occurring in the porous membrane. Okay. In the first for the first case, for the flow through membrane channel, we have got the concentration profile and obtained the mass obtained the concentration profile, evaluated the concentration profile in the membrane at the membrane surface. So, that is obtained by the film theory. So, film theory is the theory that was applied external to the membrane surface in the flow channel as Cm minus Cp divided by C naught minus Cp is equal to exponential Vw by k. Okay. Next, we will be looking into the transport to the porous membrane. First one is the Darcy's law for the solvent flux. Solvent flux, and this is also known as the osmotic pressure model. This is identical, osmotic pressure model. Okay. Now, what is that? Vw is equal to Lp del p minus del pi. Now, in this equation, Lp is the membrane performance parameter, it is a membrane characteristic. So, will be, as we have discussed earlier, we have already evaluated this permeability from a separate set of experiments. Delta P is the transmembrane pressure drop. Let us look what is delta pi is. Delta pi is pi osmotic pressure at the membrane surface minus osmotic pressure at the in the permeate site. Okay. So, what is osmotic pressure? Osmotic pressure can be expressed as a function of concentration like this: A1 C plus A2 C square plus A3 C cube. Okay. So, what is pi m? Pi m will be nothing but A1 Cm plus A2 Cm square plus A3 Cm cube. And what is pi p? Pi p will be in the permeate site A1 Cp plus A2 Cp square plus A3 Cp cube. Okay. Once we quantify this, we can really quantify what is delta pi. Delta pi will be difference of these two. So, this becomes A1 Cm minus Cp plus A2 Cm square minus Cp square plus A3 Cm cube minus Cp cube. Okay. So, now this if you look, so this equation, the second equation, the Darcy's law or the osmotic pressure model, we have constant value of Lp, we have the operating pressure delta pi delta p, and delta pi osmotic pressure difference will be expressed in terms of Cm and Cp. So, you have two governing equation, one equation for solute flux in the mass transfer boundary layer, another equation is the solvent flux for the flow through the membrane. So, we have how many unknowns? Let us see, we have three unknowns Vw, Cm and Cp, and we have two governing equations. So, two equations and three unknown, and these three unknowns are Cm, Cp and Vw. So, I stop here in this class. In the next class, we will see how we invoke one more equation in order to solve these three unknown and three equation system. Thank you very much.